My research is focused on theoretical aspects of particle physics. So most familiar are perhaps the experiments at the LHC, where protons are collided and the remnants are analyzed. However, we also need a very good understanding of what we think should happen in these collisions. These theoretical predictions are based on the Standard Model, which is basically our current understanding of how these little particles interact and behave. In case there is then a deviation from a measurement at such an experiment from the Standard Model value, it might point to the existence of new particles. However, in order to make such grand discoveries, it's essential that we have really good, very precise predictions and measurements, which both have very small error margins. Those predictions are generally made by calculating Feynman diagrams, depicting really the interaction of the colliding particles. So we started really simple, but by adding more complex diagrams, more complex interactions, we can improve the prediction step by step. Now, typically, their contribution becomes smaller at every consecutive order. In my research, I tried to improve on the way in which we deal with the shortcoming of perturbation theory, especially in the case the particles are produced on threshold. That is, when the colliding particles have just enough energy to produce the final state particle. In that case, additional radiation has very little energy and we call those emissions soft. Now, such soft emissions eventually lead to very large logarithmic contributions that really spoil the perturbative series, since all terms are roughly equally large. And in order to achieve this very complex goal, we need to make some simplifications. Now, historically, this was done by considering the leading power term in a particular expansion, but we try to improve on this by also including the next to leading power term in this expansion, eventually giving rise, ideally, to the resummation of so-called next to leading power threshold logarithms. We first studied the origins of these logarithmic contributions very carefully. Then in the next paper, we studied the factorization structure on this new level of accuracy. And those results culminated in the factorization framework for the most important logarithmic contribution at next to leading power. Now, in a final paper, we show the numerical effects of these next to leading power contributions using this factorization framework. And there we see indeed that these results can be quite sizable. So I would say this is really the main result of my thesis. Next to leading power effects can indeed be quite important for future theory predictions.